Okay, so firstly, we have the distribution table that basically is, it looks a little complicated. You will see it's not. It follows a very easy scheme. You have an Excel file and an R file that is labeled normal curve. And that basically is a characterization of the normal curve in mathematical terms, and you have happiness scores from 157 countries all over the world, and you have a PowerPoint presentation. And I would like to start with the PowerPoint presentation for now, because this will basically set the stage for what I want to show you in the spreadsheet. So again, chapter 6 in your book. First, we're going to speak about the normal curve. We're going to learn some new aspects of the normal curve. We're going to learn more about the definition of the normal curve. We will then learn how to standardize scores on the normal curve, and we will learn what that means. We will quantify percentiles and percentages under the normal curve. And we will talk in much detail about the set scores and how this is being used for hypothesis testing, which we will dig into on Wednesday. So, the normal curve. We talked about the normal curve and we said it's a specific bell-shaped curve that is unimodal, symmetric, and is defined mathematically. This is the foundation of inferential statistics. So basically all tests and everything we're discussing in this class has as the underlying assumption that we're operating with data that is consistent with a normal distribution curve. And why is this important? Because essentially we do mathematical operations with this under the assumptions normally distributed and following the rules of such a symmetric normal bell-shaped distribution curve. So it also says that the normal distribution curve is defined mathematically. And so here, this is what we have been labeling as the normal distribution curve as our frequency polygon that we have seen repeatedly. And this here is the function. So this is the mathematical function of the normal distribution curve. Essentially what it entails is it gives you an y value on the y-axis, on the vertical axis, on the ordinate, that basically is determined by sigma, which we know is the standard deviation. It's further characterized by mu, which is the mean. And then here you have a sigma squared, you have here Euler's number, and basically you have a logarithm naturalis, and you have pi. And this in its totality as a function defines this shape. So now this shape, as you have seen from the equation, is determined by the mean and the standard deviation. So basically everything evolves around this mean, and it's symmetric on both sides. And this knowledge we're basically utilizing now for hypothesis testing and to characterize a distribution, a frequency distribution. Because what you essentially can in a totality assume now is that if this frequency polygon is basically reflecting a frequency distribution of a single variable of an entire population, this means that basically this curve in its totality is the entire population. So this is 100%, which means since it's symmetric, you have at a mean of, you have a split with 50%, meaning you have at the mean, assuming it's a perfect normal distribution, you have mean, median, and mode at the same spot. Everything greater than the mean is 50%, everything less than the mean is 50%. And this, as a basic assumption and as a basic paradigm of this class, is super important. And you will see why. Good. So mathematical definition, symmetric and bell-shaped. In its totality, it's reflecting the entire distribution of an entire population, and it is defined mathematically and can as such be treated as a symmetric distribution split in half by the mean. Arithmetically, it needs to be like that because the mean is basically the sum of all individual raw scores divided by the number of raw scores. So it needs to be in the middle. Good. It's also important that when you draw a sample from your population, that sample is not necessarily looking like a normal distribution. Not at all, actually. It only starts looking more like a normal distribution if the sample size increases. The more data you have, the more likely it looks like a normal distribution, and the more likely it looks like your population. So just as an example, you look at the distribution of happiness scores in the New York City population, and you basically draw different samples from different spots in New York City. You will get hypothetically 3 different estimates of the happiness, right? That makes sense. So that's why you want a random sample. So also when your sample size, so the number of people or constituents in your sample is larger, it will be more likely reflecting the overall happiness of New York City residents. Also makes sense. And if you draw larger samples, more likely the shape will also be a normal distribution. So as the size of the sample approaches the size of the population, the shape of the distribution tends to be normally distributed, more consistent with that distribution of the population, and the mean of your sample will be more likely to be consistent with the mean of your population. Good. So that's basically the inside of that slide. So sample size really matters. And this is the graphical distribution. Likely we will not get to play around with the R code, which would have allowed for us to do exactly that what Nolan and Heinzen is doing here. So they have here a random sample of these 157 entries. They have here a random sample of 5. That looks nothing like a normal distribution, right? So you have a frequency polygon, it gives you some shape or form, but it's not really a normal distribution. However, when we increase the number and we go now to a sample of 30, yeah, looks kind of more like it. And if we increase the sample size even further and we go to 157, you have something that is quite consistent with normal distribution. Because of the bin size, it's not perfect, but it's getting there, right? So the larger the sample size, the more likely it will look like a normal distribution. However, one thing you also need to pay attention to, the more you include in your sample, the more likely you get outliers. That's also important to keep in mind, as you see here. Good. So the higher the sample size, the more likely it looks like a normal distribution. So the shape comes more like a normal curve. So potential variables that might be normally distributed, the range of potentially normally distributed variables is wide. So it can be all kinds of different variables that are normally distributed. So in my world, for example, with biologically relevant or biologically derived variables, they're pretty much most of them are normally distributed or assumed to be normally distributed. There are some that are usually a little skewed, particularly when you have 2 different states that are represented by these variables. Like I mentioned, skewed relationships with inflammatory parameters, but that's too much of detail at this point. And you need to deal with them somewhat different when you look at them analytically. The question here posed by Nolan and Heinzen is, can nominal or categorical variables be normally distributed? Think about the nature of a categorical variable. A categorical variable basically is determined by a definition. So a nominal variable specifically, if you remember the example we looked at with the visual displays of data, and we had the number of, or the percentage of Twitter, of internet users that also use Twitter. And then we had a bar graph and we had a Pareto chart, where the Pareto chart is basically ordered by the magnitude highest to the magnitude lowest. So if you have a distribution like that, even if you have a normal distribution, it could be just pure coincidence that the definition looks like that. So you can't really assume a normal distribution in categorical variables. In data like we're seeing here with histograms, it is, yeah, assume a no. I don't want to create confusion with special examples, but basically in principle it's no. So when you have now a frequency distribution with individual raw scores that you're displaying with the frequency on the y-axis and the actual magnitude of the value on the x-axis, you have the frequency polygon. The frequency polygon and its entirety is 100%. You can now do something with this normal distribution curve that is called standardization. And standardization is important because with standardization, you essentially allow yourself to do a characterization in a percentage. And you can, with the deriving STAT score, characterize the normal distribution and for hypothesis testing, the distribution of the differences of that hypothesis you're testing. But let's go back to the basic. Let's stick with the STAT score. A STAT score, as per definition, is the number of standard deviations a particular score is located away from the mean. And that's a definition, and that essentially means if you have a STAT score of +1, that's basically one standard deviation away above the mean. If you have a STAT score of -1, it's one standard deviation below the mean. Simple, right? So you know the mean, you know the standard deviation, you're subtracting the standard deviation from the mean, they have the same unit, you're subtracting one from the other, you basically get a set of -1. You add it to the mean, you get a STAT score of +1. You calculate a particular STAT score easily by calculating the individual score minus your mu divided by the standard deviation. So that is actually the mathematical operation that allows you to get it as detailed as possible, where you basically get STAT scores with decimals, and you get the individual really accurate estimate of the STAT score. And this is the point where I would like to guide you actually to the spreadsheet. And this is the happiness score spreadsheet that is part of your Canvas module today. So let's just copy this formula over. And let's look at what is needed. So we have now individual entries. We have 157 happiness score entries for 157 different countries. We have, and we can calculate the mean. That's simple, right? We have the standard deviation. That's simple too. And we have an individual X, and that's the country we're interested in. So if we were to calculate now a mean, this is simply average of B2 to B158. And this is here a mean of 5.382, which is simple, right? So we know this is our mean. We have now a standard deviation, which is now stdef.p of B2 to B158. Right, I'm copying it to the side that you can follow along. So these are basically those, oops, that's a little more. So these are the functions that basically get you to calculate the mu and the sigma. So now you have those two. So you have everything to calculate actually your first STAT score, right? And it's simple. It's super simple example. You want to have the STAT score now of Denmark. This would be equal sign, parentheses, 7.5626 minus $I, what did I do? Minus the mean divided by the standard deviation. So Denmark has a STAT score of 1.88. So if we are now locking in the reference values we don't want to change, we're just locking in $I, $3, and $I, $4. And that's the final formula that we need. So it's B2, which is happiness curve of Denmark, minus $I, $3, that's my mean, in parentheses divided by $I, $4, which is the standard deviation. So that gets you the individual set score. And now you just need to click on C2, double click the right lower corner, gets you those set scores for your entire population of countries. And what's interesting here, just look at it, and that needs to be arithmetically, that needs to be the case. Here, Turkey and Indonesia, the happiness score flips from positive to negative because 5.8382 is exactly between those two countries. So yes.
Are you able to explain how you got the Z-score on Excel again?
Yeah. You mean this formula?
Yeah.
Okay, so this is $B or B2. That's the individual entry, Denmark.
Okay.
The happiness of Denmark. Minus $I, $3. That's I3 is here the mean. So that's X minus mu.
Yeah, the dollar sign. What does that do?
That is locking in the cell. That's locking in this reference cell of the mean.
Oh.
Because otherwise, if you would pull this all the way down without locking this in, you would basically also shift this all the way down. So it would go down aligned with the actual B column, and then you don't get a useful result. So yeah, no, of course. So this is you're locking in the mean, you're locking in the sigma, and then the only thing that changes is here column B. And that gets you basically all the way down to minus 2.18. So minus 2.18 is not the happiest country. Here they're somewhat happy, average happy, and Denmark is super happy. Austria is actually considerably happy. The US is considerably happy. So it's basically you see a population mean, you see everything above is happier than the mean, and everything below is less happy than the mean. So this is how you standardize according to the STAT score. So this example, so this is how you would calculate this in the greater scheme of things. So this is how you calculate your STAT score, and you get basically an individual STAT score for each value that you're testing. So you're calculating the difference by calculating B2 minus the mean. So you get the difference, the arithmetic difference between the individual score and the mean, and you're dividing it by the sigma. So you basically get the number of standard deviation this individual value is located away from the mean, either in the negative direction or the positive direction. So simple, right? And you have here the example. So this is the height of Manuel in Nolan and Heinzen's book. So you basically you have like an average height of 70 in the class. Manuel is a little taller. He's at a STAT score of 1.5. Know how to calculate these for the exams and for the homework, please. That will be quite important. So you have STAT equals +1 is 80 with a standard deviation of 10. It's 80. -1 is 60, -2 is 50. So it follows the same principle for whatever you're quantifying. So whatever variable you standardize, the dynamic will always be the same. And you're doing that to basically compare whether you have larger or smaller based on the population mean. So the example with dogs, you have, well, a negatively sized dog and you have a positively sized dog. So you have a taller dog and a smaller dog. Basically, if you have tall and small, somewhere in the middle, that's the average dog. And so neither of these two is an average dog. So one is larger, one is smaller. That's the argument that Nolan and Heinzen want to make. So once you calculated the STAT score, logically, you can go also the other way around. So if you know your mean and your standard deviation and you know a STAT score, somebody gives you a STAT score, you can always calculate the individual score based on the Z score. So you have here X equals Z multiplied by sigma plus mu. And if you look at the formula of how to calculate the Z score, you clearly see that this is just rearranged, right? So you multiply the Z with the sigma, you can see this, and you add the mu to this product of Z and sigma, gets you to the individual X. So if I'm interested in calculating, let's say, a set of 1.5, I basically need to calculate now equal sign 1.5 multiplied by sigma plus the mu. So 1.5 is basically here. No, it's basically 7.09. Why is it so small? Okay, so that would be the way how you calculate the other way around. So you basically take the individual Z score that you want to transform in a raw score, you multiply it by your sigma, and you add the mean, and there you are. So that's how simple that is. It's a very simple principle, and will, although really open a world in the realm of statistics for you. So in the end of the day, this set distribution that you also have in your Excel spreadsheet is basically a standard normal distribution. So it's no matter what your actual score, your actual variable is, they're basically all nothing else but the distribution of set scores defined by the mean and the standard deviation. And the reason why you really do that is because it allows you to compare apples with oranges. And not only apples and oranges, it's also helpful in many other use cases. But you're comparing two things that are of interest for you to understand and to compare without these two variables actually having an inherent numerically arithmetic relationship. The example that Nolan and Heinzen show here, which I actually find very good, is emotions and the emotion of fear and the emotion of disgust. No idea what study that was, but basically it's showing it over the last 100 years, from 1900 to 2000, and it basically shows how all of these three basically all emotions and the two components, fear and disgust, have changed over time. And it shows it in the metric of a Z score, because all of these emotions would have entirely different, or should I say, matrices. It would present differently. So if you want to compare something as a general dynamic based on the population estimate at that time point, you basically can do that here by quantifying as per the population studied, and thereby you can look at it in a standardized fashion, and you can really see the different components, how the evolution over time unfolded. So that's really the way how it's being used. So you can basically show things that don't have the same metric in the same fashion and compare them to each other based on population-based matrices. So, and where Z scores are really getting important now is because we talked about the area under the curve. So this mathematical function that defines the normal curve essentially will quantify an area under that curve that adds up to 100%. That means that Z scores can also be used to quantify the percentiles in your data. And that's where it's getting interesting, because this is actually where you will be using this. So if you say, okay, you have a Z score of 0 where the mean is located, arithmetically needs to be, because the mean is the center of the Z score calculation. If you have a Z score of 1, this is one standard deviation above the mean, you will capture 34% of your data within that one standard deviation. but only when it starts with the mean. That's important because this is where the bulk of the data is, right? So you have from 0 to +1, you have 34% of the data. From 0 to -1, you again have 34% of the data because it's symmetric, right? If you go to +2 and -2, now you suddenly capture 28% more. It's actually less than 28%. It's actually, it's just a rough estimate. It's actually 95.7% you capture within 2 standard deviations above and below. And you capture with 3 standard deviations above and below, you capture within these 6 standard deviations in total, you capture 99% of data. 98.7, I believe. Yeah. So this is also called the so-called empirical rule. So that you have within 1 standard deviation plus minus, you have 68% of data. Within 2 standard deviations, you have 95.7% of data. And within 3 standard deviations, you have 99% of data. Also called the rule, and so it's the empirical rule. It's the rule of a mathematician whose name I've forgotten. I'll get back to you on that. So basically, empirical rule is what you will need to know for the quizzes. So by that, you can quantify now everything quite easily, because if you say, okay, so I have here 50%, and I can quantify now 34%, then I can also quantify what's less than -1. I can quantify this 16% too. Or I can quantify, if I know this here is actually 84%, I can quantify the 60% at the higher. Or I can quantify 84% at the lower. So this is really where this becomes very useful, because you can do it in Excel, and there are functions in Excel how you can actually quantify that. Come on. Okay, there are either functions how you can quantify that, and you can actually do that, or you can easily look it up in the so-called distribution table. The distribution table essentially starts with 0, where you have 50% of your data. That's the mean. If you go to -1, this is where your 16% are, or 15.87%. So you have here an exact outline of each entry between 0 and a standard deviation of or a set score of -1. You have, and that's the way how you have to read that. So you have the set score, the first decimal here, the absolute number, and the first decimal here on the side as a row, and you have the second decimal shown here as a column. So if you're looking for, let's say, 1.35, you need to go -1.30, -1.31, 2, 3, 4, 5. So this is -1.35. So that's how you would read that. And that's important because in many cases you want to actually do that. And we will look at a use case, a hypothetical use case in a second. So we have now the same table basically into the realm of positive set scores. So we basically have positive set scores that are above 50%. These are basically going upwards. And they're basically showing you everything to the upper end. So they're basically 84% are here, 50 plus the 34% in the greater arm. So we have now these values. And we have greater than that, you have 60%. So assuming that everything under that curve is 100%, you want to quantify 84% with a standard deviation of 1. You have everything greater than that is that 60% that is depicted here. for example. So you can, with the STAT scores, you can basically standardize and characterize the entire normal distribution curve. Good. If you're being asked, for example, and this is now an interesting use case. This is an interesting use case where you, for example, you're asked to quantify how many of your population are between a happiness score from, let's say, 7.1 to 6.5. So we have here happiness score of 7.1 and 6.5. So we want to calculate now our STAT score. So if we're doing this, we have to calculate the individual x, which is 7.1, with first parentheses, equals parentheses 7.1 minus x, which is 5.38, divided by the standard deviation, gets us the individual STAT score. Sorry, this is so small. Let me enlarge this. Is 1.51. We have now next we do the same exercise with our 6.5. So we do parentheses 6.5 minus our mean divided by a sigma. So that's 0.98. So if we are now, so these are our STAT scores. STAT scores. So now we are comparing now our percentiles. So if we do percentiles, 1.51 on the distribution table is plus 1.51. So we go 1.5, we have here 1.51 is 0.9345. That's our percentile. If we have 6.5, that's 0.982. 0.982 is now 0.98, is here at 0.8365. And if the question on the question at hand is now, how much of your population, what percentage of your population is between these two values? The only thing you need to do is to calculate the difference between this and this. And that's your proportion. If you want a percentage, you just need to calculate this multiplied by 100. So you know now that 9.8% of your population is located between 7.1 and 6.5 happiness score. So that's how you quantify this. It's a simple example, right? It's not difficult to do. It's something that you need to arithmetically go through once, and there will be examples in homework 2 to do that. That will allow for you to understand this in more detail. Please also look at it very detailed and some of the questions and also in the book. So this is a low-hanging fruit because that takes you like a minute to calculate, right? So if this comes as a quiz question, that's an easily earned correct response. Okay, great. Any questions to that? If not, then we can carry on, because now we're getting somewhere a little bit more complex. So we have spoken about random sampling. When you're drawing a sample from a population, you get an estimate of the population mean based on that mean in your population, right? So if you want to know the happiness of the New York City population, you would start off by basically going and standing with a survey somewhere on the street, and you ask 100 people, how happy are you? So you get an estimate of 100 people, what their happiness is. You calculate the mean, and you say, for that sample that I've collected, I believe that the mean of New York City is, what was it, 7.1. Good. So now you do the next sample on the other side of the city. You sample 100 people. You get another estimate of the happiness of New York City residents, and let's say it's 6.8. Then you do it again somewhere north, then you do it south, then you do it somewhere else, you do it another borough. You get different estimates of happiness. And this gets you different sample means. So now there's a relationship that when you do one sample, you mean to estimate the population mean. If you do several samples, you still try to estimate the population mean. If you get more than one mean and you have a distribution of means, the mean of these means is most likely representing your population mean quite accurately. If you're studying, it's the same principle as if you're studying, let's say you study what's going to be the most accurate sample that you can draw from the city of New York City. This is likely going to be, you study everyone, then you get an exact mean. If you study 100 people less, it's going to be a little bit less accurate. If you study 1,000 people less, it's going to be less accurate. You study 100,000 people less, it's getting less and less accurate. So what happens as a consequence, you are getting with each of your sample estimates, you get a little bit of error. And this error will create variability. And this variability is the variability you see in the distribution of sample means. Because if you draw small samples repeatedly, you get different mean estimates. And these mean estimates will vary with a variability that is related to the variability of the individual variable that you're quantifying in a population. So when you have happiness, and this is a very widespread happiness, and there's a lot of variability in the population, and you're drawing 100 different samples and you get 100 different means, and the variability in population is very wide, you get a lot of variability also in your means because it's drawn from a variable that is very variable. And it's generally less variable than individual scores. So you basically, what you get is something like this. So you have here a sample, that's one sample drawn from those 157 countries. And we kind of did it with the Ames, with the living area in Ames, Iowa, last week, Wednesday. So you draw individual countries out and you get an individual estimate of the mean in that country, and that's kind of reflective of the overall mean. If you remember, the mean of the happiness was 5.382, so that's where the mode is, kind of nice. But it shows a lot of variability. That indicates that there's a lot of variability in that overall population. If you're drawing now repeated smaller samples and you only look at the distribution of means, what you get is a more accurate estimate of the mean of your population, and you get less variability. So now there is a relationship, and you can estimate this variability of the distribution of the means by taking the standard deviation of the population and dividing it by the square root of the sample size of your sample. Meaning, think of this relationship. You have more variability in your population. There's a lot of variability. That means that your sample will be negatively affected in a way that the estimate of the population mean is going to be less accurate. Ergo, there will be more variability. So the numerator is going to be larger with a higher variability. If you draw a larger sample and you draw 1,000 people instead of 100 people, what will happen? You get a more accurate estimate of the population mean. Therefore, here the denominator, if that is larger, this will lower the variability that you assume here of the standard error of the mean. And this is a new metric that we're introducing today. That is the variability, the standard deviation of the distribution of the sample means. So this is the variability around that mean of means, where you have drawn your 50 different samples from different spots in New York City. You got an estimate of the happiness score from all of these samples. They show a certain distribution, and that distribution, that variability, is dependent on the variability of happiness in New York City and is reflected and affected by the variability of this happiness in New York City and by the size of your sample. So this standard error of the mean, which is the variability of the mean estimates, this distribution of the sample means, is affected by the variability, the standard deviation in the population, and by the size of your sample. And this is important to keep in mind, because this is what we will be using for hypothesis testing. So again, this is the standard error of the mean. That's the standard deviation found in the distribution of the sample means. So using an appropriate measure of spread depends on the use case. If you just want to understand the distribution of the raw scores, this is here basically this orange distribution. So this is considerably wide, and the blue one is basically the distribution of means. So characteristically, the mean should be the same, given that the mean estimate is equivalent to both. It is realistically not, but you assume this to be comparable, because in the end of the day, you're drawing one sample and you compare this sample to the population mean, and then you use hypothesis testing to compare that sample mean to your population mean. That's what we will be doing with hypothesis testing on Wednesday. But what's characteristically different is the distribution of the mean. So you have a slimmer distribution between the distribution of the scores and the distribution of the means. So that means that there are more outliers and that there are more extreme values as compared to the distribution of the means, because the means are already shaping towards a reflection of the population mean. So, and now we're getting actually to hypothesis. Are there any questions on the standard error of the mean? So keep in mind, standard deviation is the variability of the individual scores. The standard error of the mean is a distribution of and the variability of the distribution of the means. And these two are inherently related, but they're also inherently different from each other. And for hypothesis testing, in the simplest approach that we're going to be starting to utilize on Wednesday, we're calculating a set score, standardizing the differences between our sample mean and the population mean, standardized by the standard error of the mean. So if you have a population mean, that's a constant, right? And you're assuming now that your sample mean is this mean of means, and this variability, the standard error of the mean, is basically the variability that is to be expected around that mean of means, about your mean estimate. So this difference is basically being standardized. And if this exceeds in its percentile a certain value, which is 1.96, and this is where the 5% alpha, the 5% p-value comes into play, because you can, for hypothesis testing, you actually utilizing these differences as a probability of this being different from your population mean. So you take the difference between your sample mean and your population mean, you standardize this as a normal distribution, you get this standardized distribution of the differences, and you are basically looking at these differences at the extremes of the differences. So if the population mean is outside of this difference and it's exceeding 1.96 as that threshold below which you're facing a 2.5% probability, which is right here, 1.96, and you're taking this for both sides, you assume a probability smaller than 5% that your sample mean is actually coming from the same distribution as your population mean. So you're utilizing these dynamics to essentially quantifying probabilities of this being different from your population mean. I know this is a little complicated now at this point, but essentially it means to quantify the probability of this being a similar mean. And this is of great ramifications when it comes to hypothesis testing, because you're testing, and remember the null hypothesis and the alternative hypothesis, you're testing under the null hypothesis that the sample mean is not different from the population mean. And that probability you're quantifying, if this null hypothesis probability is smaller than 5%, you're actually rejecting your null hypothesis and you're saying, I'm accepting the research hypothesis that this is actually different from the population mean. And this is found with a set score of 1.96. And we will talk about the details on Wednesday. But basically what Nolan and Heinzen just want to show here is that there is a higher prevalence around 1.96 that basically indicates that there's quite a favorism of having results somewhere in the realm of 1.96, which basically leads to significant results. So, okay, so as a quick recap, so basically we're doing standardization. We're standardizing individual raw scores utilizing the calculation of a set score. Every raw score on your normal distribution can be quantified as a set score. It can be used to characterize the entire normal distribution curve of whatever variable you're looking at. So this is a standard normal distribution. You can thereby characterize the entire normal distribution as percentiles. Each of these percentiles are independent of the variable you're actually looking at, characterized here in the distribution table. You can look up every value of set that is representing a respective raw score. You can calculate set scores backwards by basically multiplying them with sigma and adding the mean. That's basically allowing you to calculate backwards a raw score from a set score. With the same approach, you can also quantify percentages in between two values. The only thing you need to do is you standardize them using this formula. You get a set score for each value you're interested in. You can calculate the second one, or you can calculate the distance to the mean, which is always 50%. Thereby, you can quantify the percentage that is in between those two values, and that allows you to essentially quantify the number of entries in between those two values. The central limit theorem now utilizes the same principle to relate the sample mean to the population mean. Knowing the variability of the population, you can estimate how much each individual distribution of the sample means will vary. If you are assuming that mean of your sample to be that mean of means, you can quantify the variability around this mean, and you can utilize this to standardize the difference of your mean estimate to your population mean. And thereby you can quantify the probability of your sample mean coming from the same distribution as the population mean. So you are hypothesis testing that there's no difference between the sample mean and your population mean. And quantifying this differences is the way to do that, with boundaries that are preset as per a so-called alpha value, which is your acceptable type 1 error. Type 1 error was what we discussed at the end last time, which essentially where you assume the null hypothesis to be not correct and you're rejecting it, but you actually shouldn't have rejected it. We will talk about this more in the following chapters. Okay. So that was now the theoretical part of it. Any questions to any of this? I know there was a lot of material, and conceptually it's a little, that's quite loaded actually. But it is a concept that we will repeat in more detail. And I just want to show you quickly again now what we did last time, just to make you, just to remember you the exercises we did. You remember how we looked into the Ames living areas. And we had here a histogram of living areas that were randomly sampled in samples of 60. And these distributed in that shape, and then in a second plot, it distributed more in that shape. So none of these really looked like a normal distribution. However, when we did here was the end part of the code, we quantified now 500 different means. And this is literally nothing else but 500 different means. So we're quantifying now 500 means of the same samples that we've quantified. These samples we have seen before, the histogram didn't really look like it was normally distributed, but when we look at the distribution of these sample means, and that's why I've showed you this last time, because it sets the stage for thinking about the distribution of sample means. And when you think of the mean, so if we quantify the mean of all living areas here, the mean is 1500. And you see here, if I do 500 repetitions, sorry, if I do 500 repetitions, I see here that the highest mode is here around 1500. So that is the estimate that was found by sampling a small sample and replicating it over and over and over. And we did that replication 500 times. And the mean of all these means is actually pretty close to our actual population mean. So that's where replication is important. And this distribution of the means, this is literally that standard error of the means. That is basically, could have also been arrived at by taking the standard deviation of the entire population and dividing it by the square root of 500. We would probably get a standard deviation of these 500 means that is somewhat comparable to the standard error of the mean. So this is that relationship that I meant to show with this example. All right, so this is individual scores versus distribution of the means. And the connection there is the so-called central limit theorem, which essentially is exactly that relationship between the standard deviation of the population and the standard deviation of the distribution of the sample means. That this can be related to by standard deviation divided by a square root of the sample size. Then we have here our happiness score in the R code for today. If you want to just quickly run this, we're doing the same exercise. We're building a data frame. Was 500 we're building a data frame with 157 observations. So that's that data frame that we also have in Excel. We're building now again 2 different samples, DF1 and DF2. We're looking at the means, which is 5.35 and 5.18. So again, it's randomly sampled, so there's different differences. We're seeing histogram number 1, nowhere close to a normal distribution. We look at histogram number 2. This also no normal distribution. This almost looks like bimodal in a way. But when we repeat this now 20 times, we get something that is in shape somewhat getting closer to a normal distribution, with notably a mean and a mode closer to our actual mean that we have seen in our data set, which was 5.382. So again, this is where these estimates are really shaping towards the mean. And this is important to understand and to know for hypothesis testing. All right, any questions on this? Super important concept, and please Well, try to play around a bit with the R codes because it's fun to see that kind of shaping because I meant to kind of give this as an example for you to see where that relationship actually really is. Yep. If no questions, we can conclude a little early for tonight. If any questions with the homework, I'm happy to discuss those. If not, then we can close for tonight. Wish you good night. Homework, yes. Please.
Okay, so I just met with a peer tutor to help me
Okay,
do it.
that's good.
And then, so for the
I'm
variance,
holding. All right.
okay, thank you. I'm not really sure exactly for the variance and standard deviation, does that look correct? So she said,
You don't need to calculate this. Yeah, you can do this for each group.
can I do this on the?
You just need to do it for an exam. You do it for all females and males. You don't have to do it for each of the groups. So if you read the question, it only asks you for gender-specific averages and standard deviations.
You don't need to do for the overall?
You don't need it wrong.
Oh,
No, you do it for overall male and female.
oh, no.
You're doing it for each group. You don't need to do it for each category. For each exam, but not for each range of exam scores.
Oh, it's just 50 to 100.
50 to 100, yeah, that would be.
Can't even do that.
Well, it's just the same way. You do the square deviations.
So what did I do too much? I don't.
But you did all the categories. You don't need to do all the categories. You just do
50
exam 1, 2, and 3. You do what? Let me actually stop the recording.